Julien Vovelle, scalar conservation law with stochastic forces.
Thank you, and I'd like to thank the organizers, of course, for inviting me to this conference. It is my first SPDEs conference in this perfect place, so thanks to you. And one of the organizers is my co-worker. So this is a joint work with Arnaud, and I'd like to speak about scalar conservation laws with stochastic forcing. Actually, first order scalar conservation laws with stochastic forcing. So the equation I want to study is the following one. It is du as divergence r of u dt equals phi of u dwt. So in positive time, of course. So this is a periodic. This is a n-dimensional torus. Okay. So things are simpler in a periodic setting, but we may as well work on the whole of Rn. So we will work with an initial condition in naught, which is deterministic, and which is measurable and bounded. So the unknown is a scalar. This is a scalar equation. So here A is the flux, which is a locally Lipschitz continuous function. So it is vector valued. And phi u dwt is the noise that we will specify. Okay, so in this talk, I will speak about the resolution of the Cauchy problem for this equation, and I will also explain basically why we are interested in the study of this equation. So I have to precise the framework. First, so A is a nonlinearity here, but to understand the problem, maybe it is instructive first to consider the case where capital A is a linear function. Which means that its derivative, small a of u, is a constant. So this is this equation. So for the first part of the talk, I will speak of the deterministic equation. So there is no noise. Okay. So if there is no noise and a is linear, this is simply a transport equation, and the solution is given by the transport of a certain profile u. Transport equation. And in the nonlinear case, and typically the case of the inviscid Burger's equation, for which small a of u is linear, so capital A here is a quadratic function, we can see the equation as a nonlinear transport equation. In that case, you can write, at least formally, the solution u at point x time t as a transport of the profile capital U by a speed that is depending itself on the solution. It is the effect of the nonlinearity. So this is, of course, only formal. So considering for what concerns the noise, the noise is a sum of independent Brownian motion with weight gk. So it may be multiplicative or additive. And the function gk are sublinear with respect to u. Okay. And we'll make also a regularity hypothesis. We ask gk to be to be Lipschitz continuous with respect to x, and to be a little bit better than 1/2 Hölder continuous with respect to u. So here you have a square, and we ask to have a bound with absolute value of the difference between u and v times this weight that is going to 0. Okay. These are the basic hypotheses. So whether the noise is multiplicative or additive, the nature of the equation can be quite different, or at least the way we solve it. So I will speak about first the additive noise. In the case where the noise is additive, actually you can put the noise in the unknown to confirm the equation. So this is what I wrote here. If you put as a new unknown W, which is U minus the noise here, integrated in time, you obtain a new equation. So now you have a flux that is depending on x and t via j here. So actually this is a random first order scalar conservation law, and considering the regularity of the Brownian motion, it is possible to solve this equation pathwise. So this has been done by Kim in 2003 for the 1D problem, Cauchy problem, and by Vovelle and Vovelle in 2009 in multi-dimension and for the Cauchy-Dirichlet problem. So you have also to cope with boundary conditions. Okay. So in the case where the noise is multiplicative, you can't do this trick anymore. So you have to study the problem directly. So there is a work by Feng and Nuala in 2008 in which it is proved existence in 1D and uniqueness in multi-D. So actually it is uniqueness of quite strong solutions, and they are too strong to allow the proof of existence in a dimension greater than 2. So with Arnaud we will try to solve the problem in multi-D. So this is in periodic setting, as I said, but it could be also the Cauchy problem. So I will describe this work, and specifically what we obtain is this result. We will show that there is a unique solution which has to be well defined to this problem, which is besides the limit of the viscous approximation to this equation. So you obtain a viscous approximation by adding a second order term, which is this one. Then you obtain a stochastic parabolic differential equation, which has been quite well studied. And so we show that the solution we obtain is the limit of this of the solution of this approximation as viscosity term eta tends to 0. Okay. So this is what we want to prove, and the notion of solution we consider is the following one. So I think don't look at that for the moment. Actually, this is the solution is a process which is predictable, which satisfies some bound in all LP, except for P infinity, and which satisfies this equation. So this is quite a complicated equation. I will take some time in the next slides to explain and justify all the terms here. Okay. So this is a weak equation. Okay. Okay. So I will go to explain what is called the kinetic formulation. And actually, the kinetic formulation is this equation called kinetic in reference to the theory of kinetic equation as Boltzmann-Glazov equation. So I start with a deterministic equation. So I say if you rewrite this equation of conservation as a first order PDE as follows, by introducing the derivative of capital A, you can write formally that this is a nonlinear transport equation. So you transport profile U by a nonlinear speed. So this is only formal, but there is a way to make that more correct. And the way to do that is to work not on U, but on the to add a new unknown xi and to introduce this function, which is a characteristic function of the subgraph of U. So actually, xi fixed is the characteristic function of the super level set of U. And if you try to derive an equation satisfied by F, you will obtain something interesting. So I will show you how it works. the thing is to start from the deterministic PDE, which is this one, and assume that for the moment that U is smooth, which is not an accurate hypothesis because typically the solution to this kind of nonlinear equation become non-smooth infinite time. If U is smooth, I can multiply this equation by eta prime of U, where eta is C2 function, say. So by the chain rule lemma, what I obtain is dt of eta U plus eta prime of U A of U gradient U equals 0. And if I define this to be phi prime of U, this is the definition. By the chain rule formula again, what I obtain is the divergence of the entropy flux. So this is divergence of phi of U equals 0. And now the big trick is to write every nonlinear expression of U as a linear expression with respect to this function f by considering eta as a test function. So what I do, so now you start from this, and what you notice that if, for example, eta prime is L1, you can write eta of U as a sum over R of the characteristic function of U greater than xi, eta prime of xi, big xi. Indeed, what you do here is just summing from minus infinity to U, eta prime of xi, which is eta of U. And here this is a new unknown f that I introduced. So actually what I write is that eta of U, this nonlinear expression of U, is f tested against eta prime, and this is a L2 xi scalar product. Okay, and I can do the same for phi of U. Phi of U, it is sum over R of here phi prime of xi, that is to say A of xi because this is precisely by definition phi prime of xi. So which means that phi of U is A of xi f, again eta prime. And finally, if I replace in each expression here, I obtain this equation. And so since eta prime is now considered as a test function, the final equation is the following one. Okay. And that's actually what we are interested in. Because it is easy to read the nonlinear transport on this equation. Indeed, say for example that you want to solve the Invisit-Burgers equation in 1D. So in that case, A of U is quadratic, and small a of U is U. So you start from an initial profile U naught. But now you want to work not on U but on F. So actually I have to change the graph here. So I introduce here the coordinate xi, and there is a third axis coming toward us, which is the value of F. So actually at time equals 0, F 0 is equal to 1 here, and to 0 here. Okay, so you have a plateau with a boundary delimited by the graph of U naught. here, and what tells the equation here is that at each xi fixed, you have a transport equation with a speed a of xi. So what you do is that for each xi fixed here, you let each slide moving at speed a of xi. So here the speed a of xi is xi. So what you will obtain when time evolves is this kind of graph. So here you move at speed proportional to the height here, and here you have a smaller speed. So you obtain this kind of graph. So there is a critical time t star at which you see a shock appear here. And if you continue, what you obtain is this kind of thing. And the fact is that on the last picture, f is no more the characteristic function of the subgraph of a function u. Okay, because here it is multi-valued, simply for this reason. But the fact is that you want the trick to introduce f, you can do it only if you can keep the original u from the d part. So you are faced with, once you have done this trick, you can read the nonlinear transport, but you have a new problem, which is the following one. How do you solve this equation while respecting the constraints that f is a characteristic function of the subgraph of a certain function u for each time t? So of course it means you have to deal with shocks. So the answer to this question is contained in what is called the kinetic formulation for scalar conservation law, and which has been derived by Lyon, Spertam, and Tadmore in 1994. So it can be read in this theorem, which says that the deterministic Cauchy problem is well posed. For example, in L infinity. If you solve it, so for bounded solution which are continuous in time with value in L1, and the trick is that to the transport equation here, you have to add a right-hand side, which is the derivative with respect to xi, the new unknown, of m, where m is a non-negative measure, which you don't know. You don't know m. So m is a measure with respect to space, time, and the new variable xi. So I add that actually it has to be supported, completely supported with respect to xi in this framework. So the final equation you obtain is really this one. So here you have a transport equation, and here you have, in a way, the Lagrange multiplier associated to this constraint, the fact that you have to remain the characteristic function of a graph. Okay, so when you see this for the first time, it's quite surprising, all the more since the measure is unknown. So I will give some hints on this formulation. It can be actually well understood if you look at the parabolic approximation to the deterministic problem. So in that case, so you add a diffusion to the equation, and for this equation you can write a kinetic formulation that is a PDE on the characteristic function of the subgraph of the unknown u eta. Which is the following one. So you have here the nonlinear transport, the viscous term coming from the viscous term in the original equation, and again the derivative of a measure. The fact is that for the parabolic equation, the measure is perfectly known, actually. the expression of the measure is eta gradient u square times the direct mass respect to psi at u eta. Okay. And so in particular, you can note that m eta is bounded in mass just by a standard energy estimate for the parabolic problem. Okay, since you have eta gradient u square. Okay. So you can guess that if you pass to the limit when eta tends to 0, since this is bounded in mass, you will recover a measure at the end. Okay. So I think this gives some hints on the former formulation here and the occurrence of this measure, and to show another aspect of this kinetic formulation for first order conservation law. I speak about the L1 contraction property for this equation, which we will try to get also in the stochastic case. So if I consider again this kinetic formulation, I have here a transport part, and here a term relative to this constraint. So of course the transport preserves LP norms, but it is not necessarily clear to guess what it will give concerning the evolution of the LP norm as time is going. But there is a well-known result for this deterministic equation. It is L1 contraction property, which says that the L1 difference of two kinetic solutions to the deterministic problem is non-increasing with t. Okay? And so I give you a short proof of this result using the kinetic formulation. It is quite easy to do. So it has been done by Pertam in 1998. Actually, what you do instead of looking at the difference between U1 and U2, you look at the L1 norm of the positive part of U1 minus U2, and you can switch between U2 and U1 after. And the key to the proof is this remarkable identity, which says that if you sum f1, which is a characteristic function of the superior level set of U1, multiplied by f2 bar, which is a conjugate of f2 and which is a characteristic function of the sub-level set of U2, you obtain precisely the positive part of U1 minus U2. Okay? So actually, to recover that, what you have to do is to get an equation of f1, f2 bar. Okay? So what you do, you start from the kinetic formulation for each problem here. So for f2 bar, you have to put minus m2, okay? Since f2 bar is 1 minus f2. And just multiply this equation by f2, this one by f1, sum this equation, and sum with respect to x and psi. And what you obtain is precisely the derivative of the L1 norm of the positive part of U1 minus U2 times some terms related to the occurrence of measure here. And actually, if you integrate by part, what you obtain is that you have the derivative of this function. So at least at a formal level, you can see that the derivative of this function are direct mass, because with respect to psi, you just are looking at a characteristic function of level sets. So here you have a product of measure which is not defined, but actually it has a sign, it is non-positive. Okay. So this is an elementary proof, at least formal proof, of the L1 contraction property for this deterministic equation, so always in the case where there is no noise. Okay. And it can be made rigorous just by first smoothing the equation. Okay. So actually that was the introduction, because I spoke only about deterministic equations, so I will do a brief summary before going on. So the aim is to study the stochastic scalar conversion law, not the deterministic one, but in the case of the deterministic equation, so I said that you can see the problem as a nonlinear transport equation, at least at a formal level. It can be made more or less non-formal by introducing the characteristic function of the level sets of U, F. You obtain an infinite set of linear equations, because psi is evolving in R. And to do things properly, you have to take into account the shocks, which is done by introducing this right-hand side, which involve unknown non-negative measure. So a measure which is better understood in the parabolic case, because it is explicitly known. And as I showed you, this is quite nice to prove, for example, the kinetic formulation is quite nice to prove, for example, the L1 contraction property. Okay, so now I go on, and my aim is to actually to derive a kinetic formulation for this problem. So I have to deal with first a deterministic equation with non-homogeneous source term. So in that case, the kinetic formulation for this problem is this one. So you recognize the former one in case S is not present. And here what you have is this additional term. Okay, S x t psi derivative with respect to psi of okay, so I will briefly present how you obtain this term, and then what happens when you turn to a stochastic source term. So actually, to derive the kinetic formulation for this equation, you can forget the x dependence for one moment, and just wonder what is the kinetic formulation of a simple ordinary differential equation. Actually, a scalar ODE, because your unknown has to be scalar. So this is a very simple equation, u dot equal STU. And to obtain the kinetic formulation of this equation, you have first to write the equation satisfied by a nonlinear expression of u, which is eta of u. So you just multiply the equation by eta prime. And as I did for the case of the deterministic conservation law, what you do is to rewrite this nonlinear expression of u as a linear expression of f time a test function eta prime depending on psi. Okay, so eta of u is f against eta prime, and you have to rewrite this term also with eta prime as a test function. So actually, you have to introduce a direct mass at u with respect to psi. And you should just notice that it is this direct mass is the derivative of f with respect to psi. What you obtain is this transport equation. Okay? And actually, it was in a way expected, because the characteristics equation for this transport equation are precisely these ODEs. Okay? So now you can do the same thing in the stochastic case. So now I'm watching just a scalar stochastic differential equation, du equal stu d beta t, where beta is a Brownian motion over R. And then again, to derive kinetic formulation for this equation, I have to write first the equation satisfied by a nonlinear expression of u. So this is precisely given by Ito formula. So what you obtain is first this term given by the chain rule, and the Ito correction here, which involves the second derivative of eta. Okay, so I go fast, but of course what you obtain at the end, since you have here two derivatives of eta, are two derivatives with respect to psi of f, and here you have the Ito correction, so the square of s. Okay. So now, if you skip the details, but if you do the same thing for the actually this problem, you obtain the kinetic formulation that we already saw. Okay. So the solution is solution U is a predictable process satisfying LP bond for each t, and satisfying this kinetic equation, which means that the characteristic function of U satisfies this kinetic equation when you recognize a nonlinear transport. The measure which is connected with the constraint that f is a characteristic function of a subgraph, and here the term related to the noise. Okay. Here you have the noise, and here the Ito correction. Okay. And this is the kinetic formulation, which is actually an equation which is weak with respect to x, psi, and also time. Okay, so actually you should precise what is m here because it depends on the alia omega. I will be quick on this. M is a non-negative measure. It is measurable in the sense that once it is tested against a test function, it is measurable with respect to omega. You have to assume the fact that m vanishes for large xi, okay, and to assume also that this process is predictable. And I recall you that our aim is to prove this theorem now that the notion of solution is quite clear. So we want to show that there exists a unique solution which is the limit of the viscous approximation. Okay. So before going on and showing the main line of the proof of this theorem, I just do a digression actually about this problem. So with Arnaud, we are interested in solving this problem just because it is a natural question to solve the Cauchy problem for this equation, actually to solve it globally in time. And there are also some interesting questions related to the existence of an invariant measure for this equation. And the reason being that here you have no dissipation term. You have no second order term in this equation. Okay. And so there are some works related to this problem. So a work in 2000 by E. Halin, Mazel, Chinai, in which they show the existence of an invariant measure for this problem in dimension 1 and for a Burger's flux, so a quadratic case here, which is in particular convex, plays a role. And actually to do that, they go at the Hamilton-Jacobi equation, which you do by integrating the equation. So you can do that only in the one-dimensional case. No? And of course, the case of the Hamilton-Jacobi equation is also interesting if you have in mind the case that here you have no viscosity. So there is a work by De and Souganidis in 2005 where they show the existence of an invariant measure for this multi-D problem. Actually, the case with viscosity is also considered. Okay. So now I go back to the proof of this theorem. So first, I will show you how the proof of convergence of U eta work in the framework of kinetic formulation. So the first thing I have to do actually is to derive a kinetic formulation for this parabolic approximation. So it works actually as in the non-parabolic case. And when you obtain, what you obtain is this equation. So maybe I will write the terms. So we are looking at the parabolic approximation. And I say that the kinetic formulation of this problem is this one. I think I introduce a measure here, so minus the noise. So here, nu eta is nothing but the direct mass at u eta. And this is also actually minus the derivative of f So notice that for each xt, and actually also omega fixed, this is a probability measure with respect to psi. Okay, this new here. So this is the kinetic formulation for the parabolic approximation, and I also write this estimate here, which is nothing but an LP estimates on U eta actually, just because this measure here is a direct measure at xi equal U eta. So if you sum this with respect to xi, you just obtain the LP norm of U eta. Okay. So this is an estimate on the LP norm of U eta. And besides the measure here, the kinetic measure is perfectly known. This is this term. So as I said, by an energy estimate, yes?
Can you remind what do you assume about function phi and the Wiener process?
Sorry?
What are your assumptions about function phi on the blackboard and the Wiener process? That
actually, here phi is, I forget an eta there, but actually I regularize phi for the parabolic approximation so that it is Lipschitz continuous.
But phi itself, before regularization?
Before regularization, it is a little bit more than 1/2 Hölder continuous with respect to U.
A little bit more than?
1/2 Hölder continuous.
And W? What is W?
It's a very cylindrical Wiener process, actually. I'll write it there. This is a sum of gk of U d beta k. So the beta k are independent Brownian motions. And so the gk are continuous functions. And so satisfy this hypothesis. So you assume that the square is sublinear. And this is Lipschitz with respect to x. And a little bit more than 1/2 Hölder continuous with respect to U. So actually, in the parabolic approximation, we truncate the noise to have a Lipschitz continuous dependence with respect to U. Maybe possible, probably to do better actually. Okay, so the kinetic measure here in the parabolic case is well known, and by an energy type estimate, we obtain some estimate in mass. So L2 omega, and this is the space of measure here over this set. So we have estimates, uniform estimate with respect to eta on the measure m eta, and also on the measure nu eta here. So we can pass to the limit in the certain weak sense, which I will not necessarily make precise. M eta converges to m, nu eta converges to a certain nu weakly. And as a consequence, you will also obtain the convergence of f eta, which is nu eta, the measure of the interval xi plus infinity. And this converges to a certain f, which is related to nu as follows. Okay. And now, so the key point is that the kinetic equation is linear with respect to all unknowns. Okay, so wave convergence is enough to pass the limit. Okay, so this kinetic formulation is linear with respect to the unknown f eta, and also with respect to nu here and m. Okay, so this is possible to pass the limit in this equation. So you obtain this kind of equation. which looks like a kinetic formulation, except that in the process of passing to the limit, you lose the structure of f. You don't know anymore that f is a characteristic function of a graph. And actually, this is the key point. Okay? But anyway, since I obtained this limit equation, I will be interested in this equation, which is actually the natural relaxation in a way of the kinetic formulation. Okay, so I go to what we call generalized solutions, which are defined as this as follows. So a generalized solution is a f that satisfies the kinetic formulation here, but which has not necessarily the structure of the characteristic function of a subgraph. Okay, and it has somehow a certain structure because the derivative of f with respect to psi is a measure. Yeah? Once you have fixed x and t. And you also require some estimates on u, which are the analog of the LP estimate on u. So this is what we call a generalized solution. And the fact is that when studying the limit of the parabolic approximation, we have proved the existence of a generalized solution. Okay. So now, actually, the aim is to prove that a generalized solution turns to be a simple solution. And it is important because it will give us the existence of a real solution to the non-viscous problem, and also because it will give us the strong convergence of U eta. So I will explain that point, which is classical actually in the study of first-order nonlinear scalar equation. So I emphasize, specify the type of convergence of nu. So nu, once you have fixed the area x and t, is a probability measure with respect to psi. Okay. So what happens is that this nu z, so z encompasses all the variable omega xt. So this is converging tightly once you integrate with respect to z. So, okay, so this is the kind of convergence you obtain. Okay. And the fact is that you have a relation between the structure of the limit nu and the type of convergence of U eta. So here remind that I should write it maybe. The nu eta here has a structure. Right? It is a direct mass at U eta. Okay. But a priori the limit nu has no structure. But actually there is equivalence between the fact that the limit nu can be written as a direct mass at a certain u, and the fact that U eta is converging strongly towards u, actually. Okay. So the fact is that I repeat myself. If I go back to what I obtained, that is to say a generalized solution, the fact is that showing that f is a subgraph of a characteristic function, which is equivalent to show that nu is a direct mass at a certain u. It will not only give me the existence of a solution, but also give me the strong convergence of the sequence U eta of approximate solution. Okay. So to do that, to show that this f here has necessarily the structure of the subgraph of a function, I have to give actually a kind of structural result, which says that any generalized solution to this equation is nothing but a simple mere solution. Okay? And this kind of structural result is related to the property of uniqueness for this equation. So the last thing to do to end the proof of the main result is to prove this theorem, which says that the generalized solution starting from an equilibrium, that is to say the characteristic function of a subgraph, is necessarily structured like that. And actually, the proof of this result is related to the proof of uniqueness, and for example, to the L1 contraction. So for this stochastic problem, we also have L1 contraction, which says that the difference of two solutions in L1 norm is non-increasing with respect to time. Okay, so this is a result that remains to be proved. I will stop there. We can discuss that if you want later. Thank you.
Any questions? We're going to have tea. Okay, then let's think again.